introduction. Let's go.
So I'm Frans. I'm the founder of DataProphet. I'm joined here by Jan, one of our senior data scientists, and we've just had a journal club meeting. It happens every couple of weeks at DataProphet. The purpose of our journal club meetings or journal clubs is to explore some of the fundamental kind of theories behind machine learning. And so we try and stay away from the techniques and explore the limits, the foundational grounding of machine learning. And this past session, we discussed the No-Free-Lunch theorem for optimization. It's originally put forward by David Wolpert and William Macready back in, I think it was 96. And it has
97.
97. Back in 97. And it's a very kind of interesting limitation on it. Maybe Jan, do you want to define kind of its core component? What does it say about machine learning?
So it tries to address the notion that there can be a single model to rule them all, or a single algorithm to rule them all, like a general purpose optimization algorithm that will give you the best results over all problems. And how they do this is they set up a proof, a mathematical proof, with some initial premises and constraints, where they say that assuming a finite world in which is also discrete, and where all possibilities are visited, that you cannot have one solution or one strategy or one algorithm outperform all others on all other problems, and therefore there is no universal optimization algorithm.
Yeah, I think it gets even stricter than that, where it says on average, or averaged across the set of all possible cost functions, the performance of all algorithms are equal.
Yes, correct. That is the core assertion that leads to all of the implications of the No-Free-Lunch theorem.
Yeah.
And it's also the critical point around which the proof, what the proof is trying to establish.
Yeah.
There's two papers to look at. We have been looking at two papers. The original paper by Wolpert, and then a follow-up paper that was written in 2002 that explains the No-Free-Lunch theorem by way of a different mechanism. And they state very clearly that you refer to the original paper to get all of the rigor, all of the rigorous premises. Here they just accept those premises, and they construct this fundamental matrix as a pedagogical tool. The purpose of it is to teach the No-Free-Lunch theorem. So that there's a lot of interesting outcomes, or a lot of interesting implications of the No-Free-Lunch theorem that can be explained very neatly by way of this fundamental matrix.
I think we all quite enjoyed the simple explanation.
Yes.
Yes. So the title of that second paper, as Jan mentioned, Simple Explanation of the No-Free-Lunch Theorem and its Implications, written by Ho and Pepyne. And this is published 2002, but kind of a nice introduction to No-Free-Lunch, because
yes. So looking at that paper, there are some cool things. I want to get into this. This is something that I feel is also what I would try and do in the next journal club topics when everyone's in the room. We start with like the really interesting things. The No-Free-Lunch theorem has some cases where it's applicable, and some cases where it's like less applicable. If you've defined your structure, if you solve a problem by incorporating the exact structure that you see in the problem inside of your algorithm, then the no-free-lunch theorem doesn't apply to that, because you're not treating all problems or all solutions uniformly. But if in the event of trying to extrapolate information from the no-free-lunch theorem and extrapolate from this fundamental matrix, there's a couple of things that I just really like the explanation, because it ties up so many loose ends. It feels very elegant. The two from the simple paper that defines this fundamental matrix is random restarts and ordinal optimization. It's the first two out of the applications.
Yeah.
For random restarts, which is a thing that's very often used in optimization problems, particularly anything that is sensitive to the initial vector that's fed to the algorithm. If your outcome is very sensitive to the input, you just sample many inputs. And it's like a k-means algorithm or a clustering algorithm that you apply to a problem, that you run it 10 times and you choose the best one with different starting positions.
Yeah, I think we spoke about it now, and we were thinking about random restarts in the context of some of our work, which is typically neural network based, as well as in the context of, say, the LLMs or the frontier models, because you wouldn't randomly restart training there.
Yeah.
But I think a part of our discussion was whether stochastic gradient descent, and specifically the stochasticity in it, could be considered a weak form of a restart. I don't know what you thought of that.
Yeah, I still don't have a good picture in my mind. It is a good question. I think stochastic gradient descent algorithms are less sensitive to the initial conditions because of that randomness, because you're randomly sampling from the data set in order to optimize the problem.
Yeah.
And it essentially weaker optimizations or optimizations that make stricter assumptions might be more susceptible to this sensitivity, where in the case of stochastic gradient descent, the power almost comes from its noise. If you one of the reasons why people believe, or like a mechanistic reason why people believe neural networks outperform other models, is that they stochastic gradient descent forces your optimization process to take many random steps and many varying directions.
Yeah.
And what that's going to do in aggregate is that it will force your algorithm to search for flatter minima, where the changes will not yank you out of a minimum and put you in a different place, which in a sense is a random restart. That's to say that out loud to actually picture that. Yes, that's actually
kind of a weak form of random restart. I think it's still in the area, but it's
so neural networks are an interesting thing. But the point that I'd like to make here, which I quite like about the elegance of this work, is the fundamental matrix allows you to find this using the geometric distribution, you can kind of model what is the probability of a good outcome given random restarts. And if the probability of a good outcome is assigned to P, then given your rows that all average to the same outcome over all problems, a good outcome can be found if by n random restarts to a probability of roughly n times P, given the paper, which I think is it's really well explained.
Yeah, it's quite nice to have kind of a theoretical backing and kind of quantification of the value of random restarts, right? So how many restarts do you need to find a potentially better solution?
Yeah.
And then the second thing that stood out for you was the ordinal optimization.
Optimization, yeah. I really like that, because the ordinal optimization and the later section kind of talk about the same thing. there are a class of problems out there that are known to require ordinal optimization, like the traveling salesman problem to its extreme. When you have a very large network or you've got a very large graph that you have to traverse with this with Dijkstra's algorithm to find the shortest path. It's finding the absolute shortest path across the entire network will happen according to this thing with a very low probability, where you can find the top nth percentile with a very high probability, and that top nth percentile will already give you a very short path, which is already very good, and in most cases good enough. And it is saying for these there are a class of problems where it doesn't make sense to look for the global optimum, and you really should just look for an nth order solution that's good enough within the nth percentile. And their explanation of it using the fundamental matrix is also it's very elegant. It makes use of the fact that there are y span to the power of x span minus 1 occurrences of every single solution outcome in the fundamental matrix. And the fact that you are if you're searching for the absolute best one, then you're looking for something that is you're going to do a massive search in order to find that. Where if you're looking for the nth percentile, in this case, I think they're talking about 90%. Then that probability increases quite a bit, and they actually have a formula that you can work with. It's also a geometric thing, I think.
It's a very nice theoretical
explanation. The probabilities that they state here is like less than 0.1%, and the other one is a probability of roughly 1. So they plug in some numbers to do that, but those numbers seem reasonable.
It's a nice theoretical justification for assuming a strategy of finding something in the nth percentile. Which is nice to see. The performance order is easier to determine than the performance value statement in the ordinal thing. I don't fully understand, and I need to read a bit deeper as to how it is cheaper to calculate order than value. Because that statement is made, but in reference to another paper. I don't know if that stood out.
It stood out. I haven't read that other paper, but it is also something that I also don't completely understand. Because also what's interesting is for that formulation, for that performance order section 5.2.2, they state that the reason why finding the order of performance is easier than the order finding the actual performance. In other words, without evaluating the actual performance, you can still find the nth percentile. They say that the solution space that you're looking for is no longer the span of y to the power of the span of x. It is now the span of x to the power of x, or it's only a function of x. I'm trying to find that exactly.
Depending upon the relative spans, that could be an improvement or not. It's interesting. I mean, like one wonderful paper, the simple explanation. I mean, the No-Free-Lunch Theorems for optimization, of course, the seminal work that introduced it. But I thought the discussion of insights from the fundamental matrix very interesting. I think in our journal club, we had a very interesting conversation on complexity. And complexity versus performance, and how you can drive up complexity if you want to, but it comes as kind of a double-edged sword, right? Increasing complexity will potentially give you a better outcome. So there might be a better solution to be discovered if you increase complexity.
Yeah.
But then the span of potential problems to search also increases, right?
Yeah.
And we had quite an interesting back and forth about how this might impose upon, our design of algorithms, or when you approach a problem to say, how many inputs do you consider, and what does that impose upon performance? And then, of course, in this case, it talks about fragility. Now, I also really enjoyed this paper from the perspective of it's characterizing some of these optimization and search problems as, their impact upon the design of day-to-day items.
Yeah.
Like a baby seat in a car, which is designed to solve for a specific problem, and its performance in that problem is very good, but it makes it fragile to other combinations. It makes it very fragile to other combinations, which is problematic. And actually, as a theory, this could be used to demonstrate why that occurs, right? Or that it necessarily occurs.
It's not only applied to computing problems, but also to physical systems.
Yeah.
Like baby car seats in cars, and I think they mentioned baby car seats and airbags. And then there's also one about fighter pilots. Do you wanna take us to that example? I think that's super interesting.
It's the same one, but it's the principle of it's designed very well to solve a specific problem, but it's fragile to change. Well, in that case, it's as fragile to damage, right?
Yeah.
So a very high performant item, but fragile to any small change.
Yeah.
Right? And
now
that's a trade-off.
High performance.
Yeah. And that kind of trade-off is characterized by the no-free-lunch theorem.
Yeah.
Good. Any final thoughts here? I mean, I think we're going to delve a bit deeper into this in our next session, and specifically how no-free-lunch applies to learning problems, because that's our world.
Yes.
I don't know if you had any final thoughts out of it.
Yeah, I've got some final thoughts about the two papers specifically. I feel like the theoretical justifications and the premises, the very concrete premises, are all from the first paper. But the first paper lacks a little bit in the applicability, or the giving more of a reason of why we should care about the no-free-lunch theorems. The second paper, I feel, does a very good job of giving you cases where it is seen in the wild, where there are good examples of the implications of the no-free-lunch theorem being played out. But I would love to know what David Wolpert thinks of the second paper and its implications.
Yeah. Well, can always live in hope. We're curious to get his views as well on the second one. Okay, I think we're going to wrap there, right? As always, so we run this journal club infrequently, maybe every 2-3 weeks. It really follows a principle of once enough people have read the paper, then we pull everyone in a room together and we have a good conversation. It is open to anyone who care to join, and just, I think, reach out and we'll happily share an invite. Thank you, Jan.
Thank you, Frans.
Who was the interviewer? Were you the interviewer? Was I the interviewer?
No idea, dude.
What was going on? What was going on? Were you just?
I think we were just talking.
We were just talking.
I think we were just having a conversation.
We were just talking.
Joris is our referee. You should know what's going on.
Joris, how's that for time?
Yeah, Joris,
Time
what's going on, dude?
One shot.
I expected you to be efficient.
Yeah.